Hello everyone and welcome to my channel Network Bytes with Laksh. Today we are going to start with a very important and interesting topic called OSPF, Open Shortest Path First. It's one of my favorite topics and it's also one of the most commonly asked interview questions topic as well. Right. So I thought let me share my knowledge with all of you people. So if you like this video, hit the like button and share it with your colleagues. And if you are new to this channel, do subscribe. So before we start the OSPF, I have few prerequisites that you can see on the screen. First is the understanding of IP addressing and the subnet masks, basically how subnetting is done, etc. Because that is kind of important to understand the configuration of OSPF. The second is how static IP routing works. So if you know how static IP routing works, you would understand how dynamic routing protocols work, right? So let's get started. And another thing, this may be a lengthy video, so if but please bear with me. The reason is that I'm going to explain you in depth about OSPF, and this is just an introduction. I will create multiple videos on OSPF, different parts on OSPF. So I request you to please bear with me on the length. And if you feel that the speed of my class or this video is pretty slow, feel free to speed up the playback and watch as per your own convenience. So let's get started. OSPF. Let's first of all let's understand the full form of OSPF. We all know what the full form is. It stands for Open Shortest Path First. Shortest path first. Right? So if we look at the full form itself, we can find out what basically OSPF means. Open means it's open standard, right? It's not any vendor proprietary, right? Like Cisco has EIGRP. So EIGRP is Cisco proprietary and no other vendor can use it. Similarly, OSPF is open standard. Any vendor can use it. So be it Cisco, Juniper, Aruba, Sienna, Calix, any vendor can use OSPF. That is why it's called as open, right? Shortest path first, or in short form, SPF, right? So the SPF basically stands for an algorithm, right? And that algorithm is called as the Dijkstra algorithm, right? So DJIKSTRA. I mean, he was the person who created this algorithm, Dijkstra algorithm. So first of all, what is Dijkstra algorithm? Dijkstra algorithm is used to find out the shortest path from a particular source. For example, that is R1 here, from a particular source to a destination, say R2. It's used to find out the uh, shortest path. So that's the algorithm Dijkstra. And how is this algorithm basically working? So this algorithm basically works on something called as the cost. Right? So cost is basically what OSPF uses to calculate the shortest path first, and its cost is basically formulated as your reference bandwidth divided by the interface bandwidth. About this, we will talk in detail in the later part of the video. So interface bandwidth. This is how your OSPF basically calculates its cost. So the least cost for a particular router to reach a particular destination, right? That basically becomes the best path and the shortest path. So the SPF calculation is done using the Dijkstra, and Dijkstra uses the OSPF uses that particular algorithm and finds out its cost, which is reference bandwidth divided by the interface bandwidth. Right. So this was the explanation on OSPF, and We know that OSPF is a layer 3 protocol, layer 3 of the OSI layer model, layer 3 protocol. It's classless. It's a classless protocol. It supports classless IP addressing, and it also supports VLSM. Its AD value, administrative distance value, is 110, and it uses a multicast address of 224.0.0.5 and dot 6. When does dot 6 come into picture? We'll understand that at a later point of in this series. It is also a link state protocol. So first of all, let us understand what do we mean by a link state protocol. Now, there are there are two protocols who are link state. One is ISIS, the other is link state. Now, since we are talking about link state, let's also understand the difference between link state and distance vector protocol. So, in a link state protocol, what happens is that let's assume that I have a router, right? And R1 is connected to R2, and R2 is connected to many other networks or links here, right? So in a link state protocol, R1 knows about R2's links that it is connected with. That is why it's called as a link state link. So it also knows the state of these links that R2 is connected with. It not only knows the state of the links that R1 is connected with, it also knows about the link states of R2 as well. That is why OSPF is also called as a link state protocol, right? So in a link state protocol, a router can create its own topological diagram or topological tree where it keeps itself at the center, right? Or we can call it as a tree, right? So for example, if I have four routers, R1, R2, R3 and R4, and I am running OSPF between them or any other link state protocol between them. So what would happen is that all these routers would know about each other's connectivity, meaning let's think from R4's perspective, right? R4, when he is calculating his own topological diagram through a link state protocol, he will keep himself as the at the center, meaning like he considers he R4 becomes an egocentric router, right? So it considers itself as the center of the whole network, and then it creates a topological diagram. It says that I am at the center of the network and I am connected to R3, and I am also connected with R1, right? R1 is connected to R2, R3 is also connected to R2. This is how it creates a topological diagram. And not just R4, R1, R2, and R3 will have a similar topological diagram. That means they know about how to reach each other's network. So they have the full view of the whole network. That is what a link state protocol means. Whereas a distance vector protocol like EIGRP. So let's say that R1, R2, and R3. There are three routers. They are connected and they are running EIGRP, which is basically a distance vector protocol, right? So unlike OSPF, R1 knows how to reach R3. It has its own topological diagram. But in a distance vector protocol, R1 knows how to reach R3 only if R2 knows how to reach R3, meaning that R2 will provide the information to R1 how to reach R3. In other words, R1 is dependent on R2. R1 is dependent on R2 to reach R3. Whatever information R2 is providing to R1, R1 just knows that. R1 does not know what R3 is providing or where R3 is sitting or what link is it connected to, etc. Nothing. R1 just knows and is believing the information that is provided by R2, and that is what distance vector protocol do. Okay, so this is why OSPF is called as a link state protocol, and I explained you what does link state mean and how is it different from a distance vector protocol. Now, OSPF uses the concept of areas. Right? We'll understand areas more in detail. Right. So basically, in short, areas help to divide the network in sub regions so that the information in a particular area is just limited to that area. That's just about areas. We'll talk about areas in detail at a later point. OSPF also supports ECMP, which is basically equal cost multipathing, meaning if R1 knows how to reach R2, right? And it has multiple paths to reach R2, and all the cost to reach R2 is same. It will basically load balance between the three paths. That is what you call equal cost multipathing. All right. Now, moving on, let us understand as we were discussing about link state versus distance vector. So I have come across a discussion wherein people say EIGRP is preferred in enterprise side, OSPF is preferred on the service provider side. So let's just understand why is that so. Why is EIGRP preferred in enterprise and not in service provider? And why is OSPF preferred in service provider and less on the enterprise side? Why is that so? Okay. So consider this particular diagram in front of you and just think we are running EIGRP. Okay. And basically EIGRP first of all was created to work in the enterprise side. Its main uh, design was for the enterprise side and not for the service provider side. First thing. Okay. Second thing, just imagine this is a network which is running EIGRP. Okay. And just imagine the amount of traffic that is going through this network. And let's imagine that this is a service provider network. I mean, a core network and a service provider network. Okay, lot of traffic, a lot of things that a terabyte of traffic going through each and every router. Every router is taking its own time to process the traffic to go from the egress interface to the ingress interface to the egress interface, right? Now let's just imagine one thing. If R1, if for example, if let's say the link between R9 and R7 goes down, R9 and R7 goes down, we know that EIGRP sends a query message, right? It basically broadcasts the query message, and each of these routers forward these query messages to all the other connected routers, right? Now just imagine the amount of query message that is flooding across the network, which basically will choke your service provider network, because service provider network has huge amount of data and it needs a huge bandwidth. And if your query message is basically broadcasting across your network, right, it also basically takes the processing of your routers. So what happens is that by the time, right, by the time a query response, a query request that reaches R1 up here, right, this query message is created by R9. By the time R1 has received this query message, someone in this network would have responded back to R9 with its query reply. So the query response, or the query request, sorry, the query request that R1 is getting is basically old, because R9 has already received a query response, right? Now what will happen? R1, because it has received a query request, it needs to respond, right? So R1 will again start to send its query response. And not just R1, every other router will start to send the query response. So just imagine the amount of data and the bandwidth that EIGRP takes. And in a service provider network, you have a lot of uh, hierarchical design. You have core, you have aggregation, you have semi aggregation, etc. So EIGRP in such a huge network is not suggested or preferred. And moreover, in a huge network, for example, where you have thousands of devices, 1,000 or 2,000 of devices, if you have 800 EIGRP or 800 plus EIGRP routers, your EIGRP will fail for sure. Whereas, let's imagine if we use OSPF in this matter. Okay, let's say that we use OSPF. With OSPF, what I can do, I can divide the network into multiple areas. So what would happen is that, for example, this is area number 1, area number 0, and area number 2. I know we haven't discussed about areas, but just I'm giving you an example about how OSPF and why OSPF is provided in the service provider. In OSPF, I can divide the whole network into multiple smaller areas. So what would happen is that, for example, the link between R9 and R7 here, if it fails, all the messages that flows will be only restricted in this area 0. None of the other routers in the other areas will get affected. They are running peacefully. They don't have to do anything. They don't have to do reconvergence calculation. All the reconvergence calculation will be done inside area 0. So what happens? Your network is stable. No extra messages are flowing or taking your bandwidth of the network. That is why OSPF is preferred more on the service provider side. Okay. So basically, this is also one of the interview questions: why EIGRP is preferred in enterprise and why OSPF is preferred on the service provider side. So I hope this gives you an explanation. So now moving. So let's get inside the details here. Right. So we'll start with OSPF from a single area perspective. Okay. So in a single area OSPF, okay, as I was saying, the I will discuss about area in detail in multi-area OSPF and not in the single area OSPF. Here, just imagine area as just a sub-region in which uh, a group of routers are a part of, and the information that they are sharing is confined into that area only. Okay, so we are considering just one single area, right? Multiple areas we'll discuss at a later point of time, but today we are going to only discuss single area, right? And whenever we are discussing OSPF, it is basically discussed based on the network type. Network type. So OSPF has different network types. Okay. So the first is called as point to point network type. Point to point network type. Now, what do we mean by point to point network type in OSPF? This point to point network type is always chosen by OSPF. Again, I'm stressing on the word chosen. It is chosen by OSPF if we are using a serial interface in OSPF. So point to point network type is chosen when we have a serial interface, and we know that in a serial, when we are using a serial interface, we can only have two IP addresses on the two ends of the link, right? That is why it's also called as point to point network type by OSPF. Then the next is a broadcast network type, wherein we will always commonly, not always, commonly see the broadcast network type as the default network type for any interface that is an Ethernet interface. It can be a 100 Mbps Ethernet interface, 1 gig Ethernet interface, 10 gig, 100 gig Ethernet interface, any Ethernet interface. It's considered as a broadcast network type by OSPF. Why broadcast? We know that in an Ethernet, or whenever we think of Ethernet, we think of a LAN. We know that in a LAN, we can have multiple devices connected on the same IP address range. That is why OSPF considers this as a broadcast network type. The last is a stub network. Basically, OSPF considers a stub network as a loopback interface or any other network where your connectivity is, or your network is basically getting terminated. After that, there is no connection ahead. That is where your OSPF considers such interfaces either a loopback or a network IP address as a stub network. Right. So today we'll go ahead and understand how OSPF works on a point-to-point or else in a serial interface types. So I have a diagram in front of me. So there are two routers, R1 and R2, right? Their IP addresses on R1 is 12.0.0.1/8. On R2, the IP address is 12.0.0.2/8. The loopback addresses on R1 and R2 are 1111 and 2222 respectively. So how I will go ahead with this point-to-point OSPF is, first I will show you the configuration, how configuration is done, along with the practical on GNS3 and using Wireshark. Okay, and then I'll explain each and every steps, and I will also explain how OSPF states are working when these two routers are coming up and becoming neighbors or adjacency, forming adjacency when enabled with OSPF. So let us see how the configuration on routers are done. So we know that when we configure a particular OSPF process on a router, we go into their configuration terminal, and this is specifically from the Cisco's point of view. Right? So under the configuration terminal, we type the syntax router OSPF 1. Right? This is basically the syntax for enabling OSPF on a particular router. Right? And when I do this, I write something called as a process number. Right? Now, what basically is this process number? This process number is basically uh, like the processes running inside a particular router. The router may have different types of processes running: a BGP process, EIGRP process, BFD process, CFM process, QoS process, or many other processes that are running. Right? OSPF also takes some kind of processes. So for understanding purpose, let me open the task manager of my computer. Right? So you can see that there are so many processes. You can see there are so many processes basically running on my computer. Right? Similarly, this process, right? If I am running multiple OSPF processes, so I can differentiate multiple OSPF processes using its process ID, right? So OSPF 1 means this OSPF will be using the process number 1 of OSPF. I can also run OSPF process 2 on the same router, but the difference would be this OSPF process 1 will be different from OSPF process number 2. So whatever configurations that I do under OSPF process 1 will be different and will not interfere with the configurations that I do on OSPF process number 2. That's the difference. Right? This is why we need processes. Once I write the process, I can write a router ID or create a router ID, say 1.1.1.1. Right? Now, the router ID is not necessary to be created manually, right? But this router ID, okay, First of all, we need to understand what does this router ID basically mean. Router ID is basically a kind of a name that a router chooses for itself, and it uses this router ID to introduce itself to other OSPF speaking routers. It says, I am 1.1.1.1, or my name is 1.1.1.1, and what is your name? So routers choose a particular router ID to introduce themselves using OSPF. Now, route to choose a router ID, there is an election process or a criteria. In this configuration example, I have mentioned that the router ID is 1.1.1.1. Basically, I have manually created it. If I do not enter this command, so the criteria that OSPF chooses to elect its router ID is first a manually created router ID, which we just saw, a manually created router ID. Second is that if there is no router ID created manually, then the second is the highest loopback address. Highest loopback address becomes the router ID of that router. If there is no loopback also present, then the third criteria is the highest physical IP address on the router, and that physical IP address should also be active. So the highest physical IP address becomes your router ID. So here I just, as an example, I have just created a router ID 1.1.1.1. So basically what would happen is that the moment it sees a manual router ID, these two steps of choosing the router ID will be ignored. Okay. Then the next step in creating the OSPF on a router is, give me a minute, let me erase this. So the next step is the network command. Network 12.0.0.0 0.255.255.255 area 0. Okay. Now let's first of all understand the importance of this network command. The network command serves two purposes. Okay. The first is that let's first understand what does network command basically do. When I enter the network command, okay, I give the network address or the network IP of the IP address that I want to showcase or that I want to advertise in the OSPF. Then I enter something called as the wildcard mask. Okay, I'll explain this wildcard mask in a few minutes, but please bear with the explanation that I'm going to give now. I give this wildcard mask. Now, the purpose of the network command and the wildcard mask is that wherever, okay, let me first explain wildcard mask. The reason is that if we understand the wildcard mask and the network there, we will be I can explain you the purpose of the network command. So let's go to a diagram here. So on R1, I'm creating or enabling OSPF, and I'm giving the network commands, right? So let's go with the first network command. It says 10.1.0.0 and the wildcard mask is 0.0.255.255. So what basically the wildcard mask does is, wherever in the wildcard mask there is 0, it chooses only those IP addresses. Here in this example, that is 10.1. And OSPF looks for all those interfaces whose IP address starts with 10.1. And in our example, let's check. So the wildcard mask is 0.0 and the first two octets of the IP address is 10.1. What are those interfaces which have 10.1 in its IP address? So we have 10.1 here, 10.1, 10.1, 10.1 and 10.1, right? So basically what will the network command do is that it will start to send OSPF messages out of these interfaces, right? That is the purpose of your network command, as I was about to tell you earlier. The purpose of the network command is to advertise the hello OSPF messages or OSPF messages through those interfaces whose IP address starts with these network command, right? So let's go to the next example. It says 10.0.0.0 and the wildcard mask is 0.255.255.255. So as I was saying, OSPF ignores these 255. It just checks the wildcard mask which has 0 as in the octet, and it checks 0 corresponds to 10 in the IP address, and it again checks which are those interfaces whose IP address starts with 10, and again all these interfaces starts with 10 as an IP address, and OSPF messages will be sent out of all these interfaces. The next is 0000255255. This basically I would call as the lazy OSPF command, meaning that I will use or send OSPF messages out of all the interfaces. I'm not categorizing. I'm not having a headache trying to calculate which of these IP address or interfaces should I send OSPF messages. I'm sending OSPF messages through all the interfaces, and hence I will use the network mask as 0000, right? The next is 10.1.13.0 and the wildcard mask says 0.0.0.255. So we can see these zeros corresponds to 10.1.13. So we'll have to find out that interface whose IP address starts with 10.1.13. So the only interface which has an IP address starting with 10.1.13 is this particular interface, and OSPF message will be sent out of this interface only. No other interface will send out OSPF messages. The last one, 10.1.13.1, and the wildcard mask says 0000. So basically this is all 0 0 0 0 0. So I am choosing a specific IP address through which I need to send the OSPF messages. In our previous network command, this one, the IP address can be 10.1.13.1.2.3, anything. OSPF messages will be sent out of all these interfaces because the last bit is 0 and our wildcard mask says 000 only. It is not 0 for the last octet of the IP address. That is why wherever there is 255, OSPF ignores it. It does not care, right? But in the last example, all wildcard masks are zeros. That means I am choosing a specific IP address to send my OSPF messages out of, and that interface again is this one, and through these the OSPF messages will be sent. This is the purpose of your network command, right? So let's get back to our original configuration of the point to point, right? So when I do this command network, when I enter this command 12.0.0.0 0.255.255.255 area 0, what is happening here? So basically your OSPF is choosing 0.255.255.255. So your 0 corresponds to the first number in the IP address, that is 12. So it looks for those interfaces whose IP address starts with 12, and in our scenario This is that interface, and R1 starts to send OSPF messages out of this interface. So the network command has two purposes. First is to send OSPF messages, or in short, we call it as OSPF hello messages. I'll explain about hello messages in some time. OSPF hello messages, and also listen to those hello messages and listen to those hello messages as well. Is there anyone who is sending hello messages to me on that interface? This is the first purpose. Second purpose is to advertise that particular network. Advertise, in our scenario, advertise the network 12.0.0.0 network, 0/8 network, right? So any IP address which is a part of 12.0.0.0/8 network will be advertised in this network command. This is the purpose of your network command, right? Similar kind of configuration will be done on R2, right? Where I will say configuration terminal, router OSPF1, router ID 12222 in this case, and network is going to be the same, 12.0.0.0, 0.255.255.255 area 0 is going to be the network command. And again, OSPF in this case will look for the IP address that starts with 12, and in our scenario, this is that interface, and R2 will start to send OSPF messages through this. Let's look into this through a practical. So you can see I have two routers, R1 and R2. It's just the same two routers with the IP addresses that you can see. So on R1, let me show you the interface IP addresses. Show IP interface brief, exclude unassigned. You can see on serial 4/0, the IP address that is configured is 12.0.0.1. And on R2, show IP interface brief, exclude unassigned. Sorry, show IP interface brief, exclude unassigned. We can see the IP address is 12.0.0.2 on R2. There, I have not created loopback addresses yet. I will create in some time. Okay, so let's also open Wireshark and start to capture these OSPF messages. Okay, and let me also enable and debug commands on these routers. So on router R2, debug IP OSPF packets, debug IP OSPF hello messages, debug IP OSPF events, and debug IP OSPF adjacency. I'll do a same debug on the other router, debug IP OSPF packets, debug IP OSPF hello, debug IP OSPF events, and debug IP OSPF adjacencies. Right. So now let me enable OSPF on R1. So configuration terminal, router OSPF 1. And if I just give a question mark, we can see the process ID can be given from 1 up till 65535. So I'm using a process ID of 1, right? And the moment I did this, we will see OSPF is enabled. OSPF, you can see it says OSPF, creating OSPF process 1. That means I have enabled OSPF. I'm still not sending OSPF messages, or I would say that OSPF hello messages. Okay, OSPF hello messages. Right now, on R1, I will type the network command. I'm not giving the router ID first. I'm not giving the router ID. Okay, I am allowing OSPF to choose the router ID. Network 12.0.0.0, 0.255.255.255 and area 0. Now we will see R1 starts to send OSPF hello packets. As I was saying, OSPF sends messages at a multicast address of 224.0.0.5. Okay. So the moment you enable OSPF and start to send OSPF messages through this network command, OSPF starts to send hello messages. Hello OSPF messages at the multicast address of 224.0.0.5, and it is sent at every 10 seconds interval. It is sent at every 10 seconds interval, and we can see that OSPF sends hello messages at 186, then it sends at 196, then we will see it will send it at 206 or 205, because this is going in microseconds, so it is 205, right? And we can see the same thing on R1 as well. R1 is sending hello messages out of its serial interface 4/0, right, at a multicast address 224.0.0.5 and with a router ID 12.0.0.1. Okay, we know that, as I was explaining, the router ID has three criteria to choose. First is a manual router ID. If the manual router ID is not present, the second is the highest loopback address. If the highest loopback address is also not present, the third is the highest physical IP address. And in our scenario, I did not create a loopback address, and hence R1 chose 12.0.0.1 as its router ID, and we can see that 12.0.0.1 is the router ID. Okay, we will not hear OSPF messages being received on R2. Why? Because I have not enabled OSPF on R2. That is why R2 is receiving OSPF messages, but it is not responding to it. Why? Because I have not enabled OSPF on it. We can see R1 is sending OSPF messages at 224.0.0.5. That is the hello packet. Right. Now let's just understand what is inside this hello packet. Okay. In this hello message or hello packet, we will see few of the most common uh, information. First is the router ID of this router or R1, which is 12.0.0.1, right? And the network that it is advertising, right? That is 12.0.0.0, and the subnet mask, that is /8, right? Then the area that it belongs to, we have mentioned that the area is 0, correct? The hello timer, we have I have mentioned that the hello messages are sent at every 10 seconds, so it will also tell about its hello timers, about in the inside the hello message, that is hello timer, and it will also tell about its dead timer. Now what is dead timer? Dead timer basically means, if once, let's assume that R1 and R2 have formed OSPF adjacency, they will keep sending each other the hello messages at 10 seconds. But for some reason, any one of them stops to send hello messages, the other router will wait for 40 seconds. Will wait for 40 seconds before declaring the other router as dead. Right? So these are the few common information that we'll find inside the hello message, and let's check the hello message created. Right. So inside the open shortest path first, we'll see the OSPF header. We'll see this is OSPF version 2. We can also see it's an hello packet, and we can also see the OSPF router ID, that is 12.0.0.1. The area is 000, right? And what is inside the hello packet? It says the network mask of the network that it is advertising is 255.0.0.0, right? And so as I had mentioned, it would show, it would tell about its dead timer, router dead timer, that is 40 seconds, right? Which is basically hello timer times 4. You can see that. So these are the common message that you will find inside the hello message. Okay. Now, similarly, let me also enable OSPF on R2. Let me enable OSPF on R2. R2 would also send the same OSPF messages, right? OSPF R2 would also send the same OSPF messages. Okay, so I'll do the same configuration terminal, router OSPF 1. I will not create a router ID. Network 12.0.0.0.255.255.255 area 0. Let's see what happens. So on R2, configuration terminal, router OSPF 1, right? Network 12.0.0.0.0.255.255.255 area 0. Now, the moment I did this, we can see there are a lot of messages that are flowing, right? That are flowing between the two routers, right? So now let's understand this flow. We understood the configuration, right? Now let's understand what happens behind the configuration. Once you do the configuration, how two routers are becoming OSPF adjacent. Let's understand that. And so, as I was saying, when you enter the network command, the two routers start to send hello messages to each other, correct? So when they send hello messages to each other, inside their hello message, right, they have their router ID, which is 12 here. The router ID is 12.0.0.1. Here the router ID is 12.0.0.2, correct? Now, for the two routers to become OSPF neighbors and adjacency, there are few criteria. First, their area should be same. Area should be same. So if you had observed, I created area 0 on both R1 and R2, right? They should be from the same network. They should be from the same network, right? That is, here I said on serial 4/0 of R1 12.0.0.1 and on R2 12.0.0.2/8, right? So they both are from the same network. So they are from the same network, right? The router IDs should be different. The router IDs are different. Here it's 12.0.0.1 on R1 and on R2 it is 12.0.0.2, correct? So and the hello timers should match, meaning that R1 should send hello at 10 seconds interval, R2 should also send hello messages at 10 seconds interval. Their hello timer and dead timer should match. Correct? Now, with this, we are going to start the OSPF states. OSPF states. So we know that R1 has sent a hello message, R2 has also sent a hello message, and we saw there is a lot that happened, right? There is a lot that happened here. If you see, there is a lot that happened here on R1 and R2 as well, and we can see the same on the Wireshark as well here, right? So I'll explain each and every of these steps now. That is a part of OSPF states. So again, moving on with the OSPF states. Again, if you're liking this video up till now, hit the like button, share, and uh, share it with your colleagues and friends. And if you're new to this channel, please do subscribe. So when they send hello message, let's say assume that uh, R1, I enabled OSPF on R1 first. So what R1 does is R1 sends a hello message, right? We saw it sends a hello message where it mentioned its router ID, right? And it said my router ID is 12.0.0.1. Okay, and it goes into a state called as init state, meaning initialization state or initiating state, right? Init state. And it is also, as I said, when it is sending a hello message at the first, it is also listening to any other hello messages. So it is also basically listening, since it's listening to any other hello message, and because R1 initiated it, it has not seen any other, it has not seen any other router IDs. So basically that's a question mark, right? Now on R2's side, on R2's side, when it when I enabled OSPF on R2, it also moved into an init state. But when it moved into an init state, it sent out its hello message where it says that my router ID is 12.0.0.2 and I have not seen any other router ID, right? That is basically a question mark for it, right? Now, when when R1, here let me write down R1 and R2. When R1, right, when R1 receives the init message or the hello message from R2, right? So it sent out a hello message and it is receiving another hello message from another OSPF speaking router, right? So basically what would happen is that it will go into a state called as a two-way state. Two-way state when it hears about another, it hears another OSPF messages, right? Similarly, R2 would have already moved on into two-way state before even sending the OSPF hello message. Why? Because R1 was already sending OSPF message to R2. The moment I enabled OSPF through the network command, it received the hello message. It, instead of moving into an init state, it would have moved directly to a two-way state. And that we can see here. If you see on R1, let me undebug this, undebug all. Here also undebug all. So if you see here, R1 is continuously sending hello message at the multicast address 224.0.0.5 from the router ID 12.0.0.1, correct? And it received a hello from 12.0.0.2, right? And area 0 whose router ID is 12.0.0.2 as well, right? And it is saying send immediate hello back to that neighbor, right? So it sent a hello to 24.0.0.4, right? And what is happening? They moved, I mean, R1 moved into a two-way state. R1 moved into a two-way state. A similar communication we can see on R2 as well. Two-way communication to 12.0.0.1 state two-way. So as I was saying, when the two routers see each other's hello messages, they go from an init state to a two-way state. This two-way state is basically called as neighborship. Two-way neighborship. They are not adjacent. They are neighbors. Two-way neighborship. Right. After a two-way neighborship has happened, they move to a state called as X start state. X start state. Now, what is this X start state? Okay, this basically X start state is basically telling the telling each other that they are about to start the exchange of their database. So if you remember, as I was saying, in a link state routing protocol, the routers exchange their database, then only they know the whole network topology, right? So after a two-way state, they move to a state called as X start, meaning that it is the start of the exchange of database. But before the start of the exchange of your database, they negotiate on few things. And what are those things? First is that they need to elect a master and a slave. Master and a slave. Okay, master and a slave. So what does master and a slave mean in OSPF? It means that one of these two routers has to be a master, the other has to be a slave, meaning that the master will always initiate the exchange of database and the slave will receive it, and upon receiving the database from the master, the slave will respond or send his own database to the master. We'll understand this step in the next state, but before that, let's move on in the X start state. As I was saying, in X start state, the two routers have to negotiate on few things. First is who is going to be a master and who is going to be a slave, and whichever router has a higher router ID, that router becomes the master. So in our case, R2 has a higher router ID because 12.0.0.2 is higher than 12.0.0.1, and hence R2 becomes the master and R1 becomes the slave. So if we check, here, as I was saying, on R2, it says neighbor negotiation done. We are the master. We are the master. And on R1, it will say we are the slave. So whosoever router is higher, router ID is higher, it becomes the master, right? And on Wireshark also, we can see the same. This is sent by R2. I am opening R2's OSPF messages, and it we can see that it says I am the master. It says I am the master, and we can see that the ms bit, that is the master bit, is 1. ms bit, that the master bit is 1. R2 says I am the master. We can also see that R1 would also say that I am the master, because there is still the negotiation is going on between the two routers. R1 is also saying I am the master. R2 is also saying I am the master, right? Then on the next stage, we can see that the master bit is now not set. It's 0. Previously, the master bit was set to 1 on R1. On R1, the master bit was set to 1, but now on R1, the master bit is not set to 1, because now it has accepted that it is the slave, right? Then the second thing that they negotiate is the DBD sequence number. DBD sequence number. So what is DBD first? As I was saying, OSPF creates a database inside the router, and that database is basically exchanged with each other, right? So before the two routers become OSPF neighbors or adjacents, they exchange a small summary of their database with each other. Okay, and that summary is called as DBD, or database descriptor. Database descriptor. This is what DBD means, database descriptor. Okay, and the sequence number of this DBD is also decided in this state, that is X start state, right? So, and who decides the state? Who decides the sequence number? Master, right? So, if you see here, if you see in our state, R2 R2 says I am the master. I am the master, and the sequence number that I am choosing is 4044. I am the master and I am choosing the sequence number 4044. R1 also says I am the master, I am choosing the sequence number 2931. But then when R1 says that I am the slave, which when it says I am the slave, it accepts the sequence number that was created by the master, that is 4044, that is R2's sequence number. So sequence number of the DBD exchange is also decided. Then the last factor that is decided is the MTU. MTU of the two routers is also decided, or not negotiated, is also agreed upon. So what happens is that if R1 and R2's interface have two different MTUs, the OSPF gets stuck at the X start state. I can show you that now. But why is MTU important in the exchange of your DBDs? The reason is that DBD is basically a data, right? And if the MTUs are different on both the routers, the DBD will basically be fragmented, right? And we do not want fragmentation for a particular database. That is why it's recommended that on the two routers, your MTUs should be same. Let me show you, if I change the MTU, what will happen. Okay. So show IP OSPF neighbors. If I do, we can see that it says 12.0.0.2, which is R2, is in the full state. Now let me change the MTU on R1. Configuration terminal, interface serial 4/0, IP MTU 1400, right? And let's see if it changes the state. Show IP OSPF neighbors. We'll see that it's still in the full state. Though I have changed the MTU, it's in the full state. This means that once the OSPF adjacency has formed. When OSPF adjacency formed, the state is full. When the OSPF adjacency is formed, there is no meaning of MTU. MTU does not matter. MTU matters when you are creating a new OSPF adjacency. So let me clear the OSPF process here. OSPF process, clear IP OSPF process. Sorry. Yes. Okay. So now let's me show you show IP OSPF neighbors. We'll see it is stuck at the X start state. It is stuck at X start state. Okay. On R2 also, if we see here, okay, I have shut down all the debugs. Let me uh, turn on the debug for adjacency. Debug IP OSPF adjacency. Right. Debug IP OSPF adjacency. We can see here we are receiving the DBDs from R1, but it says neighbor 12.0.0.1 has a smaller interface MTU and the state is stuck at X start. Right. So that means we need the two MTUs on the routers to be the same. Otherwise, it will get stuck in X start. This is a very important interview question as well. What happens in the X start state of OSPF? So three things happen. A master and a slave is decided, and the DBD sequence by the master is decided, and the MTU is negotiated. You can ignore the MTU if on R1 I say show, sorry, configuration terminal interface serial 4/0 IP OSPF MTU ignore. When I do that, we can see the two routers will form adjacency. See, the two routers have moved on from that state, X start state, and now have gone to a full state. When it's a full state, that means your adjacency has been formed. We can do that. So in the X start state, your master slave is decided, your DBD sequence is decided, and the MTU is decided. Right. Now, the next state, after your X start state, we can see there is something called as exchange state. Basically, X start means starting of the exchange state. Right. So the next state they go on is called as exchange state. Both the routers go into the exchange state. Exchange state. Now, in the exchange state, what happens is that R1 and R2 they both exchange their DBDs. Okay, with the sequence number that was decided here, and since R2 is the master, it will send a link state update with its own DBDs. Now, what is DBD? As I was saying, DBD is a small summary of the database that R2 has. Now, what is a database? Database is a collection of networks that a particular router is connected to or knows about. So let's say R2 knows about 10 network, 20 network, 30 network, and 40 network, right? All these networks, it will share a small description or summary of these networks with R1. Because R2 is the master, R2 will initiate this database exchange or DBD exchange, right? So what R2 does, it sends a link state update to R1 with one of its DBD. In response, R1, which is the slave, sends a link state acknowledgement with its own DBD. So let's say R1 also has some DBDs to exchange. It also sends its own DBDs. So when What happens in exchange? R2 and R1, they will exchange their DBDs, only DBDs with each other, only DBDs with each other, right? So once they have exchanged their DBDs, they go into a state called as the loading state. Loading state. Now, for example, let's say that on R1, it knows about 50 network, 60 network, 70 network, and 80 network, right? So in your exchange state, R1 has sent small DBDs of 50, 60, 70, 80 network to R2. R2 has exchanged 10, 20, 30, 40 network with R1. Now, again, in your loading state, they will exchange the whole database of these networks with each other. Again, only the master will send the data or database to the slave, and in response the slave will send his own database to the master. Until and unless the master sends a request, a slave cannot respond. The slave cannot initiate a database exchange. It is initiated only by the master. Master always initiates the database exchange. So until and unless the link state request is sent by the master, a slave will not respond. We can see that in the Wireshark. See here, R2 asks for link state update, for which R1 responds link state update. Again, a link state update is asked by R2, R1 responds, right? So the master requests or sends an update for which the slave responds, right? Now let's take an example. Let's take an example. R1 has R1 knows about 90 network, 100 network, and 110 network as well. Okay. So as I was saying, the master can only request for some updates, right? When it has sent its own updates, the slave will respond. So now what happened? R2 sends the update for 10 network to the slave. The slave responds for 50 network, right? It received the request and it is responding with its own database to the master. The master then sends the update for 20 network. The slave responds back for 60 network. Then again an update for 30 network comes from the master. The slave responds with 70 network. Again, there is a request or an update for 40 network. The slave responds for 80 network. Now, the slave still has 3 more networks to exchange with the master, but the master has completed his exchange. So the master is not going to request for more updates because he has shared his own network database with R1. He does not need more updates because he has shared his own database with the slave. But slave has 3 more network database to share with the master. How does the slave tell about this to the master? This is where we have in our database description something called as the more bit. We saw the master bit, right? Here, this is R2, which says I am not the master, so that's the slave, right? More bit. This more bit means that I have more DBDs to share with you, right? So whenever the slave is responding back to the master, it sets the more bit to 1. it sets the more bit to 1. Here also it sets the more bit to 1. Here also it sets the more bit to 1. When this is received by the uh, master, master now knows that I have shared all my database with the slave, but the slave still has more database to exchange with me. So the master basically sends an empty DBD or empty database to the slave. Slave then responds with his own network information, setting the more bit to 1. And thus, finally, when the slave has sent all its network information, that is 110 is the last network database that it wants to share with the master, it sets the more bit as 0. Let me see if I can find that on the Wireshark. See here, we can see it says more bit is not set. That means it has exchanged all its information. It has exchanged all its information with the master. It has no more information to exchange, and that is why now both of them have exchanged their whole database with each other. Now this is happening inside the loading state, right? Once all the database is exchanged, right, they go into the state called as full state. They both move into a state called as full state, which we can see here, loading to full. So when both the routers have completely exchanged their database with each other, they go into the full state. And when they go into the full state, they are called as OSPF adjacent routers. So if we see here, it says OSPF adjacency. And if I do a show IP OSPF neighbors, we will see the state of the neighbor is full. On R1 as well, if I do a show IP OSPF neighbors, I'll see the state as full. So this was about OSPF. This was just an introduction to OSPF. I still have a lot to discuss on OSPF and in depth, just like in this video. So if you liked this video, hit the like button, share it as much as possible, and please do subscribe to the channel. And have a great day. Thank you.